Hey guys, so continuing here, you might remember I mentioned that collisions are the most typical problem or type of conservation of momentum problem. But there's really two broad categories. So it says here interaction between two objects will fall into two broad categories. One is collisions, and this is very straightforward. Objects collide when one goes against the other. Now, they don't have to necessarily go against each other. They don't necessarily have to be head-on. It could be that this guy just has a much faster velocity and that guy maybe isn't moving, or maybe it's moving but slower. So as long as they sort of go into each other in some way, it's a collision. The other type doesn't really have a very obvious name, so I kind of made this up. I call this a push-away situation, where instead of two objects coming together as they would in a collision, they're pushing away from each other. Okay, so there's some examples here. Throwing or recoil. So if I throw something, I'm pushing the object that way, but because of Newton's third law, action-reaction, as I push the object's pushing back on me. So we're both basically pushing away on each other. Every time you throw something, you're pushing on the object pushes you back. If you are on frictionless ice and you throw something that way, you're going to move back. Okay? Same thing with recoil. When you shoot a gun, you're pushing the bullet that way, therefore the gun gets pushed back this way. Same thing with mutual pushing. If you have the classic example is two ice skaters face each other and they push away and they both move away. Now if you think about it, recoil and throwing are both cases of mutual pushing. When you throw something, you're pushing on the object and the object is pushing against you. It's just that in the case of skaters, they both are like people, they're not objects, right? So they're not innate objects and they're sort of applying force on each other through their muscles and whatnot, as opposed to on a box. If you throw the box away, it's pushing on you because of a reaction force. Cool? So it's a little bit different, but you can think of it as being the same way. And the last example is an explosion. So if you have an object and if you have a bomb and it explodes and it breaks into two parts, one part's going to go this way and the other part's going to go this way. Or if one part goes that way, the other part's going to go directly opposite this way, that it forms a line. And that's because when the bomb explodes, these parts are pushing away on each other. So all of these are really just different variations of mutual pushing problems where things are pushing on each other. So typically, in a lot of these problems, the two pieces or the two things or the two people are initially at rest most of the time, and they will push away on each other here, and then they end up going in opposite directions. Okay, so you can have collisions and you can have push away problems, and the nice thing is that they both work almost the same way, and we're going to look at both of them. Okay, so in problems it says here where objects are interacting, and usually you're just going to have two objects interacting. You might get a bomb explosion problem that splits into three fragments, or a three-way car collision, but a vast majority of the time you're only going to have two objects interacting. So when we have that, we're often going to use the conservation of momentum equation. So whenever you think two objects interacting, collision or push away, which is sort of the opposite of a collision, I want you to immediately think of conservation of momentum equation. Okay, so I'm going to show you what the conservation of momentum equation is. Conservation of momentum means the momentum is conserved, doesn't change. So P initial is the same as P final. Now, because we have two objects, this is P initial of the system, P final of the system, right? So this is actually P1 initial plus P2 initial, and this is P1 final plus P2 final. It's not that the individual momenta are conserved, it's the combination of the two that's conserved. Remember also that P equals mv. So my last step here is going to be to replace every one of these guys with an mv. So instead of P1 initial, it's going to be M1 V1 initial. And instead of P2 initial, it's going to be M2 V2 initial. And on the other side, it's the same thing, except I got finals instead. M1 V1 final plus M2 V2 final. So M1 V1 M2 V2, M1 V1 M2 V2. This is the conservation of momentum equation, which is the most important equation in this chapter. And whenever you have two objects interacting, that's what we're going to use. All right? So that's the conservation of momentum equation. You got to know it. Let's do a quick example here. We have two balls moving towards each other. Ball A moves with 7 to the right, again, if they're moving towards each other, if you're moving and the ball is moving to the right, that ball is coming from the left. So A, 3 kilograms, moving with 7 to the right, and B, 4 kilograms, is moving with 5. It doesn't say that it's moving with 5 to the left, but you're supposed to figure that out. You can figure that out by knowing that they're moving towards each other. If one's going one way, then the other has to be going the other way. Because they go in opposite directions, they have different signs. Please don't forget the signs. A lot of people make that very silly mistake, very simple mistake. As soon as I write the 7 and the 5, I immediately put the signs to make sure I don't forget. Okay? So these balls are going to collide. It says after the collision. So this is before the collision. So I'm going to put a little hashtag before here. It's like an Instagram picture. After the collision, B moves with 2 to the right. So after the collision, B is going to move with 2 to the right. Therefore, it's plus 2. Okay? We don't know what's going to happen with A, and that's exactly what we want. We want to know the magnitude and direction of the velocity of A after the collision. After the collision means V final, and we're talking about A, so it's VA final. What is VA final? So, do we have two objects interacting? Yes, this is a collision. So what do? We immediately jump into the conservation of momentum equation right up here. Let's do that real quick. I'm going to write the long version of this equation first. M1v1, M2v2, M1v1 final, M2v2 final. Now, if you do this a lot, it's going to get kind of tiring to write this stuff over and over. So what I actually do is I don't write the full version of the equation, and sometimes professors want you to start with the full version of the equation and then plug in numbers, so then you have to do it that way. But if you don't have to do it that way, if you can start plugging in the numbers right away, what I like to do is I look at the masses, 3 and 4, and instead of doing this, I just go 3, that's mass 1, space, 4, 3, 4. So I save some time by not writing this entire equation. I just do 3, 4, 3, 4, and I put spaces for the velocity. So and then I have to figure out which numbers go here, and then I got to look at the picture. So next to the 3, this is the 3 right here. The initial velocity of the 3 is a 7. That's a plus 7. The initial velocity of the 4 is a minus 5. The final velocity right here of A, I don't have. That's what we're looking for, VA final. And the final velocity of B is plus 2. So if you look at this equation, I got a bunch of numbers, one unknown. I can solve this. We're done. So this is going to be 21 plus negative 20 equals 3 VAF plus 8. Right? So this is 1. This whole thing here is a 1. And then to solve for VA, I'm going to send the 8 to the other side. It goes as a negative 3 VAF. And I'm going to skip one step here. This is just algebra. Actually, I won't skip a step. So 1 minus 8 is just negative 7. And then I have to divide by 3. And the final answer is negative 2.33 meters per second. Now, if you look at the question is asking for the magnitude and the direction. And what do you think the direction is? And hopefully you said left. It's just to the left. And we know that because of the negative sign. We said that going to the right was positive. Therefore, going to the left is negative. Okay? So this ball is going to go this way, which kind of makes sense. If they're going this way and then this goes this way, you would expect that A would go to the left. Now, that doesn't always happen. That's not always the case. So you can't really assume that. For example, if you have a bowling ball and a ping pong ball and they're going with the same speed towards each other, they're not going to bounce and then go back this way. The bowling ball is much heavier, so it has much more momentum. So what's probably going to happen is after the collision, well, actually what's definitely going to happen is that after the collision, they're just both going to move that way. The bowling ball might slow down by a tiny, tiny bit, but they will keep going in the same direction. Here, they had similar speeds and they had similar masses. In fact, the momentum of this guy here is plus 21, and the momentum of this guy here is minus 20. So one wasn't much more overpowered than the other. And in this case, it makes sense that if one goes to the right, the other one goes to the left. Cool. That's it for this one. Let me know if you have any questions.